4. We're introducing a new topic today called related rates, and this will actually be related rates part 1. We'll be doing 3 lessons on related rates, looking at different word problems and how they can be applied to calculus and the derivatives. So the problem I'd like to start with is, everybody knows during a zombie outbreak, if you hide in a room with a locked door, zombies are going to start showing up at the door, and they're going to show up at a certain rate. And here the rate is 1 zombie per minute. The force that these zombies can apply to the door is equal to this equation F, and we'd like to know how quickly the force on the door is changing after you've been hiding in the room for 25 minutes. If we look at the wording of this question, specifically how quickly something is changing, that word quickly implies time, or the change in force over time. So we're looking for the derivative of f with respect to the derivative of time, df by dt. But if I look at my equation for force, there's no variable t. So how are we going to solve this question? How are we going to answer this question? The way that we can approach that question of how quickly the force on the door is changing is by using the principle of implicit differentiation. And we saw that the other day. We could take the derivative of certain variables with respect to other variables. And as we approach these problems and as we read these problems, there's some strategies that we can use to make solving them easier. In a related rate problem, the very first thing you should do is draw a diagram. Once you've drawn a diagram, take the time to state what you know. And as you are stating what you know in these problems that we're being given, we want to find derivatives. After you've listed the things we know and found some derivatives, you should state what you need to know. What are you solving for? Okay, doing these 3 things will help you solve these related rate problems. So we'll come back to the zombie problem in a minute. We're going to start actually with something easier. So in this problem, we have a raindrop falling into a puddle, and as it falls into the puddle, it creates a ripple that spreads out from the center of the circle. And that center is where the raindrop hit. And we can observe that the radius of the circle is growing at a rate of 3 centimeters per second. And we'd like to use this information to figure out how quickly the circumference of the circle is increasing with respect to time. So I can represent this with a diagram. I have some raindrop being dropped in a puddle, and it creates ripples out from the center. So these ripples are moving outwards from that center point. And that line obviously is the radius of the circle. So some things that we know just from reading this question, we know that the radius is growing with respect to time. So the change in radius with respect to time is 3 centimeters per second. We're being asked to determine the rate of increase of circumference of the circle. So we know that the circumference of a circle is equal to 2 pi r. We're dealing with time here. So if I find the derivative of my equation for circumference, I'm going to do it with respect to time. So the change in circumference with respect to time, dc by dt, is equal to 2 pi times the change in radius with respect to time. So this is everything that I know from the question. What am I trying to find? What do I need to know? Well, I need to know the change in circumference with respect to time. I'm trying to find dc by dt. Well, if I know dr by dt, I can take dr by dt and sub it directly into my equation for dc by dt. So this is going to become dc by dt equals 2 pi times dr by dt, which is 3. So when I simplify this, dc by dt is changing at a rate of 6 pi centimeters per second. Okay, so we'll write that up as a therefore statement. Circumference is increasing at a rate of 6 pi centimeters per second. And as we work through these problems, try your best to keep your answers exact. So this is probably the easiest example of a related rate problem. Let's go on to something a little bit more challenging. Here we have a balloon being filled with air such that the volume of the balloon is increasing at a rate of 3 pi meters cubed per second. We want to find the rate at which diameter is increasing with respect to time after 12 minutes. So again, we have a balloon that's being filled with air. As we fill this balloon with air, obviously the radius of the balloon is going to increase as the balloon gets larger. And let's see what we know just from reading this question. We know that volume is increasing, so the volume is changing with respect to time at a rate of 3 pi meters cubed per second. If we're dealing with how volume is increasing, we're going to use the volume of a sphere, and the volume of a sphere is 4/3 pi r cubed. Which means, if I take the derivative of this with respect to time, volume is changing with respect to time at a rate of 4 pi r squared times how quickly the radius is changing with respect to time. We're looking for the rate at which diameter is increasing with respect to time after 12 minutes. So we need change in diameter with respect to time at 12 minutes. In my previous example, once we had set all this up, we were able to simply just substitute this information into the equation where it was needed. But if I do that substitution, I still have two more unknowns in my equation for dV by dt. So I need to do something to get rid of one of those two unknowns. We're trying to solve for this. We're trying to solve for dr by dt. So since we're trying to solve for dr by dt, we need to somehow eliminate the variable r squared. And we can do that by using this information, using the fact that we're trying to find the change in diameter with respect to time at exactly 12 minutes. We know that if the change in volume with respect to time is equal to 3 pi meters cubed per minute, and I just noticed a mistake in my question. That should be per minute. Per minute, sorry about that. We know that if the change in volume with respect to time is equal to 3 pi meters cubed per minute, at 12 minutes, volume will be equal to this rate of change, 3 pi, times however many minutes have gone by. So at 12 minutes, the volume is 36 pi meters cubed. If we know the volume at 12 minutes, we can also find the radius at 12 minutes. So the volume at 12 minutes is 36 pi, and that's going to be equal to 4/3 pi r cubed. And I can simplify this by isolating r. Some terms will cancel. So I'm left with 27 equals r cubed. And if I take the cube root of both sides, the radius is equal to 3 meters at the 12-minute mark. So now I know everything that I need to solve this problem. I know that dV by dt is 3 pi, and that's equal to 4 times pi times my radius squared times the change in radius with respect to time. Again, simplifying this, 3 pi over 9 times 4 times pi is going to be equal to dr by dt. Canceling some of these terms out. I'm left with 1 over 12 equals dr by dt. But we wanted the change in diameter with respect to time. And we know that diameter is twice the radius, so I can multiply the change in radius with respect to time by 2 to get the change in diameter with respect to time. that. Which means that my change in diameter with respect to time is 1/6. So diameter is changing at a rate of 1/6 of a centimeter. Sorry, let's keep our units consistent. 1/6 of a meter per minute. So let's just go back to our initial problem just to answer this. I'm not really going to draw, well, I guess I could draw a diagram. There's the door. There's the zombies arriving at the door. There's zombie skew. And they're arriving at the door at a rate of dz by dt. And we know dz by dt is equal to 1 zombie a minute. We also know that our equation for force that the zombies are exerting on the door is equal to z squared minus 0.5 z. We are trying to find, we need to find the change in force with respect to time, df by dt. So I'm going to take this equation for force and I'll find the derivative with respect to time. So df by dt equals 2 times z times dz by dt minus 0.5 times dz by dt. Again, we have a similar situation to our second example. We have one equation. We can plug some things in for this equation, but we'd still end up with 2 unknowns. So we also need the number of zombies at the door after 25 minutes. Well, if they're arriving at a rate of 1 zombie per minute after 25 minutes, there'd be 25 zombies. So plugging all this in, df by dt is going to be equal to 2 times the 25 zombies times the rate at which they're arriving, which is just 1, minus 0.5 times the rate that they're arriving. So solving this all out, I get 49.5, and forces in newtons per minute. So force is changing. Force is changing at a rate of 49.5 newtons per minute. Okay, so when you come to class tomorrow, there'll be some opportunities to practice questions similar to these. Every day we're going to kind of introduce some different types of related rate problems so that by the end of the next 3 days, you'll have a lot of different questions that you have strategies to solve.